Welcome to the lectures on fundamentals of MIMO wireless communications. We are currently exploring diversity gain. We have discussed several receive diversity. We have also discussed several transmit diversity. We have also explained to you the general notion of diversity. So what I'll begin with is a bit revision of the general notion of diversity and see the implications that were presented. So some minor or some fine conclusions that can be drawn yet from that. And once we discuss that, we'll move on to the transmit diversity mode that are still remaining for us to explore. So when we look at the typical explanation of the diversity scheme, where we said we are having several parallel transmissions, and these could be time, frequency, or space, and where the signal energy was divided equally amongst all the transmitted sequences. What we had found out was the probability of error expression was less than typically, as we usually use. We used n e bar e to the power of minus gamma bar d mean squared by 4m and hf squared. This is what we use. This m is coming because of this m over here, and when we carried on to calculate p e bar, we had found this to be n e bar using the MGF method or whatever method you would like to use. Gamma bar d mean squared by 4m, and last time we explained this could be beta m by 2 m to the power of minus m, right? And here we explained about the order of diversity. Now so as m increases, your diversity gain increases. We have also said that if this is the performance of no diversity, then this is the performance of one order of diversity, two order of diversity, and so on. So the slope increases as m increases. This is what we have explained. So now in this the beauty of this particular description that we have is the total transmit power is remaining the same because of this, because transmit power per branch is es by m, and if I add up all of them, like 1, 2 up to m, I'm going to get es, that is es by m multiplied by m is equal to es. So that is the total power. So we can compare this with the case where it is CISO, that means a single input single output system, where also it is es. So the SNR over here is es by n naught. Here also the effective SNR is es by n naught. So the total average SNR is the same in both the cases. That means once we take the CISO case or we take the multiple input, the parallel transmission where we have diversity. So here is a nice case to compare. So when we move to other cases where it was not pure, where it was not the es by m scenario, we did not have this m in the denominator because of the m here. For transmit MRC, this m got compensated. For STBC, this m remained, and there was like 8 in the denominator, as you might remember from the other expressions. So anyway, back to this expression. This is pure diversity. There is no array gain expressed in this. That is fundamental. There is no array gain in this expression. There is only diversity gain, which is here. So as es increases, as number of branches increases, per branch SNR decreases. So only diversity gain is expressed in this. Now in this, we would like to study the limit m tends to infinity. This is a very, very important condition that we are saying, that suppose I increase the number of transmissions to infinity while keeping the same constraint on transmit power. What we mean is that suppose I have a single antenna to transmit, single antenna to receive. So here the total transmit power is es and average SNR is es by n naught. Compared to this, I consider a situation where I still have es as the transmit power, yet I send several of them. What is going to happen? I am not going to change the average transmit power, neither am I changing the average received power. So average SNR of this link is remaining the same. There is no array gain. So still what happens? So effectively I am enjoying an average es by n naught. So what's going to happen in that? So for this, what we need to see is that if we take limit n tends to infinity 1 plus x upon n to the power of n, this is the thing, this tends to e to the power of x. We use this identity. Using this identity, if we say limit this tends to infinity, that means ideally the expression that we have is n e bar 1 plus gamma bar d mean squared by 4m raised to the power of minus m. So basically we have minus m over here. So we say m tends to infinity. This expression would boil down to Pe bar is less than or equal to any bar e to the power of minus gamma bar d mean squared by 4. Now if you'd see this expression is independent of m, and this is the same as the expression of error probability for AWGN. If you look at it, any bar e to the power of minus gamma bar d mean squared by 4. So this is the expression for AWGN. What does it mean effectively is that if I keep on increasing the order of diversity, the slope increases, and finally at a certain point when it tends to infinity, it meets the error probability for AWGN. And you can clearly see this because we made the we started off with PE is less than or equal to NE bar Q of root over d mean squared gamma bar by 2. This was the expression that we started with. So this, if you use the Chernoff bound, this turns out to be NE bar e to the power of minus gamma bar. I'll write it bigger. This expression, I can bring it here, let's say NE bar e to the power of minus d mean squared gamma bar by 2 times 2 is 4. So this is the same expression as this one. So once we get from this Q function and as limit m tends to infinity. So what we have said is as the diversity order increases without array gain, that means we don't require array gain, still we would meet the performance of a AWGN system. That is very, very important to remember, that as we increase the order of diversity, we are actually going towards the performance of AWGN. However, one word of caution, that if we have array gain, that means if this m is not there in the denominator, if you have array gain, in that case along with this increase in slope, this curve would also shift to the left, and in that case you would beat the performance of AWGN. It would be better than that. But however, again, there is a way around that. If somebody might say that well, I want to compare the composite SNR, that means after combining whatever is the SNR in AWGN, if I put equivalent the same amount of SNR in AWGN and try to look at the average or the combined SNR in case of combined scheme, in that case AWGN is going to beat that of the combining scheme. However, if we keep the average SNR per branch as the basis for comparison, if there is array gain, definitely it will be better than AWGN. Whereas in the other case, when there is no array gain, what we just saw, the combining schemes would reach a performance limit which is the same as that of AWGN. This is very, very important for us to remember. So this is very nice. With this, we'd like to move on to transmit diversity schemes. So we have already described one transmit diversity scheme, that is the Alamouti scheme. In the Alamouti scheme, we have already said there are 2 transmit antennas, and we are going to transmit S1 and S2 and S2 conjugate minus S1 conjugate. So this is the scheme that what we were transmitting in case of transmit Alamouti. And when we transmitted this particular scheme, we actually sent minus S2 conjugate and S1 conjugate. We had only one receive antenna. So now instead of having just only one receive antenna, could we have a scheme where we have 2 receive antennas? So that means we have H11, this would be H21, this link would be H12, this would be H22. So this could be a little bit modification of the earlier scheme. In the earlier scheme, it is Alamouti with 2x1 combination, 2 transmit, 1 receive antenna, and then we move on to a 2x2 system. So although we specify it as 2x1, the H matrix is actually 1x2, and in this case it is a 2x2. So that we should be clear. So when you say 2x1, we are actually meaning 2 transmit, 1 receive antenna. and when we are mentioning the H matrix, the number of rows is indicating number of receive antennas. So we should be careful when we are noting this. So if we have the Alamouti scheme with 2 receive antennas, then what's going to happen? In this case, the H channel is basically H11, H12, H21, H22. This is the H channel, and the Y1 signal that we are going to get, we would write it as root over ES by 2. The same ES by 2, we are going to transmit the same symbol sequence. There is no change in the symbol sequence. We are going to have H11, H12, H21, H22, and the symbol S1 and S2, and we are going to receive them in 2 antennas, N1 and N2. Now, while we discuss Alamouti scheme, we should always remember that we are sending the symbols in 2 time instants, T1 and T2, and we have used the coefficients H1 and H2 in that case. Now we are using H11 and H12, H21, H22. It is very important to remember, we make the assumption that coherence time is greater than 2 symbol durations. So if this is symbol duration 1, this is symbol duration 2, it should be greater than that, so that the channels remain constant across the 2 symbol durations. That is very, very important for everything to hold. In the second interval, we receive this second vector, and that is again ES by 2. We have the same channel matrix H11, H12, H21, H22. Remember, in the previous case we had H11 and H12. We did not have this. In this case, we are having this. Ideally speaking, it should be at time T1, and this should be at time T2. Ideally speaking, this should be the case. But if we assume this even at T1 and T2, they are the same. That's the assumption. And here the signal is minus S2 conjugate and S1 conjugate. So this is a special construction that is done for the scheme Alamouti. Rather, this is N3 and N4, or rather it is N1 at time T2, N2 at time T2. So this is the overall signal space that we have, and the signal that we need to construct is Y1 vector followed by Y2 conjugate. So if we construct the signal in this way, we will be able to decode the signal that is being transmitted. So this is what we did in the previous case. We will do in the same situation. So this is indicating time instant 2, and this is indicating time instant 1, but the 2 entries of it, that means Y1 and Y2, Y1 of T1, Y2 of T2, are basically the inputs at the 2 antennas, Y1, Y2 at time 1, and again Y1 at time 2, Y2 at time 2. So that is how the overall expression is. So this is what we need to construct. So if we construct that expression, the one that will be led to is Y, the big Y, is equal to root over ES by 2, and you have H11, H12, H21, H22, and then H12 conjugate, H11 conjugate with the minus, H22 conjugate, and H21 conjugate with the minus, just like we had in the previous time, S1 and S2. See, we are taking a conjugate of Y2. If you are taking a conjugate of Y2, this will become S1 and S2, the minus sign would be absorbed. So we take in the minus sign inside it. The expression would appear in this form, plus N1, N2, N3 conjugate, N4 conjugate. Right. So so it's basically again Y equals to ES by 2 square root H effective times this is a matrix times a vector plus N is this vector, this is the S vector, this is the H effective matrix. And again, the way we decode it is we simply multiply H effective Hermitian with Y, and you can guess what's going to happen is that this Hermitian means this is going to come in the row. So basically this is going to get multiplied by itself. So it will be H11 squared, H21 squared, H12 squared plus H22 squared, which is the Frobenius norm of the channel matrix H effective. And if you take the cross elements, that means this multiplied by this, you are going to get the terms which are going to cancel out each other. So H11 conjugate times H12, and there would be again minus H11 conjugate times H12 over here. So they are going to cancel out with each other, and the effective expression that we are going to get out of it is Z is equal to root over ES by 2 mod HF squared I of 2, because this is a 4 cross 2 matrix. So if we do this, so we are basically doing H effective Hermitian times H effective. So this is a 4 cross 2 and this is a Hermitian, so it is a 2 cross 4. So effectively we are getting a 2 cross 2. So that is why we have identity matrix of size 2 plus n tilde. So this is the whole expression which we get from this. Again, you have to calculate the SNR and Zi, any particular symbol. So this contains two symbols. This is a 2 cross 2 matrix. So S1 and S2, the estimates that we get, ES by 2 HF squared SI plus NI tilde I equals to 1 to 2. So this is what we have, and if you have to compute the SNR for this, we first have to consider E of n tilde Hermitian, which would turn out to be HF squared times n naught times I of 2. So that is going to be this, and basically you have HF squared multiplied by n naught as the noise power, and here also we have that. So HF squared in the denominator, this whole squared, so one of them goes off. So gamma combined would turn out to be HF squared. ES by n naught would definitely come, which we could write it as gamma bar, and this 2 would remain in the denominator. Now this expression looks the same as the earlier case. However, HF squared has changed. In the previous case it was H1 squared plus H2 squared. That means in the Alamouti 2 cross 1 case. In this case it is H11 squared plus H12 mod squared plus H21 mod squared plus H22 mod squared. So basically this is a bigger number. So if you would take the expected value of this, in this case it is 2, in this case it is 4. So that means here the size is more and you have a bigger value to this. So moving on to forward with the error probability expression, what you're going to get is probability of error. Average expression of that going by this would be any bar gamma bar d min squared by 4m, if you remember. So this would give us a 2 to the power of minus 4, because here HF squared has 4 entries. So there are 4 entries in it, and the pi that we had, pi I equals to 1 to m t mr, or 1 to m. In this case it was 4, so that gives us this 4 over here. This 2 is the value of m, because we have two transmit antennas, because of which we had ES by 2. So this is the because of the diversity that we are getting, and that 2 is leading to this 4, because we had 4m. M is the number of transmit antennas in that case, so that is leading to 8. So this is the average probability of error expression, and if you would look at the combined SNR, this would be the average value. You're going to get it as gamma bar expectation of HF squared by 2. So as we said, this value is going to be 4 by 2 times gamma bar, that is 2 times gamma bar. So now you have twice the SNR of the CISO case or per branch SNR. So if we compare the error probability curves, we would have the probability of error curves in this case. If this is the curve for probability of error for no combining, and if we just have 2 cross 1 diversity, let's say Alamouti 2 cross 1, so this is going to be the one. If we have this 2 cross 2, it will be somewhere there with this additional increase in diversity gain because of the order 4 that we have over here, and much better than this thing. And additionally there is additional SNR gain because of two receive antennas. So we have this 4 order of diversity, and we have this two 2 times increase in average SNR. So we have an array gain in this case, as well as we have the diversity gain. So we have exploited all the fold branches in diversity gain, and we have also used up the 2 receive antennas for achieving array gain compared to the previous case. So this is another method, and you can simply go on and keep on adding antennas at the receiver in order to have more and more array gain into the system. So as long as you keep your transmit antenna with 2, the same processing algorithm should help in getting the appropriate diversity gain and average array gain that we are looking at. So with this way, we can obtain diversity gain even without providing channel state information at the transmitter. With this, so basically this mechanism, if you would see carefully, we have multiple input and multiple output. So we have 2 antennas at the transmitter and 2 antennas at the receiver, the minimum number required for MIMO communication. And yet we have obtained a 2 plus 2 order of diversity. In this case, that means all the 2 times 2, that is 4 order of diversity. That means all the antenna branches have been used in this case. However, in this case there is no CSI that is sent. Without CSI, without channel state information, we have obtained this. Now we would like to move on to the scheme which uses channel state information at the transmitter and tries to obtain this performance. So we are still at diversity. And in diversity, what we will be looking at is multiple input, multiple output. We have already seen such a scheme, but in this particular mechanism, we will say that the channel state information is known at the transmitter. So it is known at the transmitter. So we will consider a system which has, let's say, MR receive antennas and we have MT transmit antennas. So basically it's a MR cross MT channel coefficient. So we could write the expression of the received signal as the vector y, which is MR cross 1 is equal to root over ES upon MT. So that is ES upon MT times H matrix times weight or weight vector at the transmitter times S, which is the signal. So remember at this point, when we are doing diversity technique and we are doing CSI known at the transmitter, we did already one thing, which is the transmit MRC. So in that case, we had sent the symbol S across all the antennas, but they were weighed by appropriate weight vectors or coefficient and sent to the different antennas. So because we are sending actually one data, we are actually talking about diversity. In case of Alamouti, we had S1 and S2 and S2 conjugate minus S2 conjugate and S1 conjugate. So here you could argue that we send 2 different symbols, but overall in 2 different time, T1 and T2, overall we have sent 2 symbols. So that means per symbol time we have sent 1 symbol. So overall we have actually not gone to something known as the multiplexing, although it appears to be multiplexing, it's not multiplexing, which we'll see later. So at this point, all I'm trying to say is when you're doing diversity, you're basically sending the same information across all the different branches or the different paths that exist. So we have this S over here plus noise. So this is also MR cross 1, and this would be spatially white. That means 0 mean, circular symmetric, complex Gaussian, spatially white. We could add this thing. And this is MT cross 1. We have an MT again to ensure that the total power is maintained. So that means we would put the criteria W must satisfy the Frobenius norm of W squared is equal to MT. Remember, we said this is the total strength of the particular matrix or the vector that is there, and this is to maintain total average transmit energy or power constraint, and we would consider a receiver Z is equal to G Hermitian Y. So basically these are the equalizer coefficients, and this would be of course MR cross 1, and this Y that we have, yeah, G is MR cross 1, so G Hermitian, and when this is Hermitian it is 1 cross MR, right? It is 1 cross MR. G Hermitian is 1 cross MR. This is MR cross 1, so there is a product between them. So the end result that you have is basically 1 cross 1. So this is recovering S in that case. It's going to get back S. So this is what we have to do, and G is the complex weight vector. It's the complex weight vector at the receiver. So we have W at the transmitter, and we have G at the receiver, and when we do this MIMO based diversity gain with CSI known at the transmitter, we have to choose W and G in such a way that we maximize the SNR, and that's our objective. And we'll see in the next lecture how do we maximize this SNR, and what do we get at the end when we maximize the SNR following a special scheme, and that will require you to revisit the linear algebra and the important part of singular value decomposition based factorization of matrices. So we'll be using some of the results from singular value decomposition, which will help us in the derivation of the result for this particular transmission scheme. Thank you.